Okay, welcome to part 3 of the video. So I'm going to leave the slides and the theory behind a little bit now and have a look at how you actually go about calculating some commonly used useful coordinate systems and transformations using AstroPy in Python. So this part of the talk will also sort of act as an introduction to the exercises that you'll do after this talk later on in the day. You'll be given a version of this Python notebook, which has some examples of how you can do useful things in AstroPy, and then it will have some exercises for the student at the bottom for you to complete as well. Okay, so as I mentioned earlier, the last thing you want to spend your time on in most cases is rewriting lots and lots of complicated code and calculations to do these kind of astronomical coordinate transformations yourself. I mean, you can do it in principle. You can get the textbook out and code everything up. But again, you know, the scope for getting it wrong is quite high. And there's just normally better things to do in your research career. So there are commonly available astronomical libraries in many, many different languages, and there are many of them. Today I'll just talk about AstroPy, which is one that's commonly used in Python. So I'm just going to give you an example of the kind of things you can do in AstroPy. You can certainly do more than I'm showing you here. If you actually look at the documentation on the internet for AstroPy, it will give you a list of all of its capabilities. So I'd be very surprised if anything you want to do isn't already covered by quite simple AstroPy functions. So here is some examples. Let's just jump in and start using it. So first thing is we can define. Let's define an astronomical object in the sky, and let's define its coordinates on the celestial sphere. So let's choose the Orion A, which is a molecular cloud in Orion, which you might observe with a radio telescope. In equatorial coordinates, so that celestial sphere, right ascension and declination, it has the following coordinates. So the right ascension is 05 h for hours, because again right ascension is measured in time weirdly, 35 minutes 17 seconds, and the declination is -5d for degrees, 23 minutes of arc, which I'll talk about in a minute, and 28 seconds of arc. So that's the coordinates of the object that you might be interested in. So you can look that up from many of the astronomical database websites. So for example, NED, which is one that's run by Caltech, right? So in AstroPy, you need to first of all include the SkyCoord libraries using this from AstroPy coordinates import SkyCoord command, and then you can set up an object which represents the a Python object which represents the object in the sky in this way. So we can use the SkyCoord function, supply the coordinates here, right ascension, declination, as a string, hence the quotes, and call that Orion, right? And then Python has capability so you can just print it out and it'll just give you useful information. So what that actually does is say it's a sky coordinate object, and the right ascension and declination in degrees is as follows. So what that's done already is actually converted the time format right ascension, i.e. 05 hours 35 minutes 17 seconds, into decimal degrees, which is 83.8 degrees, which makes sense because we know that 6 hours is going to be 90 degrees, so that makes sense. And then the declination is -5 degrees 23 minutes 28 seconds, and that in decimal degrees is that figure there. So that's already useful. And again, you can do things like change the you can access this information individually. So, for example, Orion.dec.degree is the declination in degrees, as you might expect. And then you can also do unit conversion, so you can actually convert that to radians. So by specifying the declination and then two-string units equals radian, u dot radian, you can get that number in radians if you want. So you can have minus 5 degrees, which is minus 0.09 radians. So the declination is minus 5.39 degrees and minus 0.09 radians. So you can do basic degree radian unit conversion in this package, and you can just print out the values for the coordinates there. So that's kind of useful. The really useful thing is that immediately you can start printing out the values of the same object in different coordinate systems. So, for example, there is in the same way that there is a equatorial right ascension declination system, there is also a coordinate system based on the disk of the Milky Way, the galactic coordinate system, which has galactic longitude and galactic latitude in a similar way to the Earth has latitude and longitude. This has galactic latitude and galactic longitude. So you can do very easy, quick things like print Orion.galactic. It will tell you what the galactic coordinates are for this object. So where it is in a spherical system that's based on the plane of our Milky Way. So again, that's very useful. So and very quick to do. So this is great, but we've not really gained much information here. We supplied it the right ascension declination, and we can get the galactic coordinates, which is great. What would be more useful to us, though, is if we knew where this object was on the sky at a certain point on the Earth at a certain time. Right? This is the most common kind of celestial coordinate transformation you want. You know the right ascension and declination of the object, so you looked it up in a catalogue, for example. That's not going to change. But you want to know, is it above the horizon tonight? Has it already set? Can I observe it? Where is it in the sky? Where do I need to point my telescope? So this kind of thing is a fundamental coordinate type transformation that you'll do very commonly in astronomy. So the way this is done in AstroPy is first of all, we need to import a couple of the libraries, the Earth location part, to define an Earth location, a location on the Earth. And what we can do is define the Kuntunze, I hope I pronounced that correctly, location, just by supplying the latitude of the location and the longitude of the location on the Earth. So if you're at any position on Earth and you know where you are, the latitude and longitude, you can set up an Earth location object in this way and give it a name. U.degrees just tells it that the units are degrees for that, right? So, and then what you can then do is again do a coordinate transformation very easily on that. You can you've supplied latitude and longitude. You can also get it to return something in what's called a geocentric coordinate system, which is an XYZ Cartesian coordinate system centered at the center of the Earth. So imagine a center of the Earth. You do print Kuntunze geocentric, then that will be, let's get this right, 6,346,000 meters in the X direction from the center of the Earth, that number in the Y direction, and that number in the Z direction. Not massively, perhaps, useful, but interesting to know that you can do that transformation very easily. Okay, so we defined a coordinate on the Earth, this latitude and this longitude. So that's where we're going to be observing from. So that's easy enough. The other thing we need to do is create something in AstroPi that knows what time it is, so that it can actually see, where the zenith or any point in the sky is on the celestial sphere, because the Earth's continuously rotating. So this is essentially, it's continuously rotating and obviously going around the sun. So what you can observe depends strongly on what time it is. So we can define a time object by importing the library for time, and then using the time constructor function. So that would be the year 2017, April 24th, and then the time is 1400 hours. And if I say location equals Contunze, that means that that's the local time. So that would be the time that you would locally be looking at on your watch, as opposed to universal time, Greenwich Mean Time, or any of the other commonly used time measures in astronomy. So that is 2 o'clock in the afternoon. So we can then print that out, and it just pretty much returns what we gave it. So that's fine. We can work out the local sidereal time, which I'll talk about later, and the at that time, which I'll talk about what that means later on. And we can work out what the hour angle is for the Orion objects, again, which I'll talk about later on. So I'm not introduced that yet in the lectures. The most useful function is basically to use the what's called the alt-az function, which gives you the altitude and the azimuth of the object at your location at your specific time. So this really is 9 times out of 10 what you care about. You've looked up your object in your catalogue, it has that right ascension and that declination, and you're saying, can I observe it? Is it above the horizon, i.e. is the altitude above 0? Because if it isn't, you won't be able to observe it, because it'll be below the horizon. And where is it on the sky, so that I can point my telescope towards it if it's, very simply, if it's got an altitude and azimuth time mount. So to do this, we create the sky coord object Orion as we did before, and then we call a method on it called transform2, and then we supply alt-as at the time that we defined earlier. Obs time equals time, so that was the time that we defined up here, and the location being the location Contunze, which we defined again earlier. So there's a location on the Earth, and there's a time, a local time. So then from that, there's lots of hidden machinery in these Python libraries to work out exactly where that's going to look like on the sky at your location, right? So it'll tell you what the altitude is, i.e. the angle above the horizon, and what the azimuth is, i.e. the bearing on the compass points, if you like, the angle between the north direction and this object. So to do that, then we just call that function, one line, and then just print it out, again, one line. And then if you want to access the altitude separately, you can do altaz.alt in degrees, round it to 2 decimal places. And so when we print out the whole object, we get a whole bunch of extra information, like, for example, the geocentric coordinates, some other stuff, and then the azimuth and the altitude, which is what we're interested in. So the altitude there at that time is 65.78 degrees. So that's nice. That's nice and high in the sky. So that's definitely observable. So then we could then just point our telescope 65 degrees above the horizon at that compass bearing, and we would in principle see the object that we want. So these are the kind of calculations that you have to do time and time again when you're preparing observations for a telescope. Often all of this code will be built into the telescope software anyway. So sometimes you can just supply a list of of right ascensions and declinations and times and things, and then it will calculate everything from there. But in practice, this is what I was talking about earlier about doing the calculation yourself by reading up all of the contents of the textbook on spherical astronomy to go from right ascension, declination to altitude and azimuth would be quite a lengthy calculation to do, with lots of scope for error. So in this Python tool here, we can just do it in really what is very small number of lines. So there is some exercises for the student, which I won't talk about now, but one of the exercises will be to complete the table of the coordinates of the NCP and SCP at various locations that we talked about earlier. And then there'll be some exercises using this code to work out the positions and the altitudes and azimuths and so on of a different astronomical object. But the principles that you'll be using will be the same as what's illustrated here. Okay, I think I'll leave it there for this part, for part 3. Thanks.